The moon is leaving, not dramatically, not visibly, 3.8 centimeters per year, about the rate your fingernails grow. But it's moving away from Earth, consistently, measurably, every single year. And we know this not from theory, not from calculations, but from laser beams we've been bouncing off reflectors left on the lunar surface since 1969. The moon appears fixed, permanent, the most reliable feature in the night sky. It's been there every night of every human life ever lived. We've written poetry about it, navigated by it, built calendars around it. It feels eternal. It isn't. Nothing about it is static. And the mechanism pushing it away is something so ordinary, so familiar, that you've seen it every time you've stood at a beach and watched the tide come in. The ocean is pushing the moon, has been for 4.5 billion years. And that fact, once you follow it all the way through, changes how you see the moon, the tides, the length of a day, and the expiration date on one of the most spectacular natural events Earth has to offer. Let's start with tides. Because the picture most people carry around is wrong, not completely, but enough to miss the interesting part. The standard explanation, the moon pulls the ocean toward it. There's a bulge on the side of Earth facing the moon, high tide under the moon, low tide on the sides, and the Earth rotates through this pattern, giving you 2 high tides and 2 low tides per day. That's half the picture. There's another bulge on the far side of Earth, directly opposite the moon. And that's the part that makes people pause. Why would the ocean bulge away from the moon? Here's the actual mechanism. Gravity isn't uniform across an extended object. The moon pulls harder on the parts of Earth closer to it and weaker on the parts farther away. The near-side ocean is pulled toward the moon more strongly than Earth's center. Earth's center is pulled toward the moon more strongly than the far-side ocean. The result? The near side gets pulled away from Earth's center, and the far side gets left behind relative to Earth's center. Both sides bulge outward, not because the far side is being pulled toward the moon, it's not, it's being pulled less, and that differential is enough to create the second bulge. This is what tidal force means. It's not the strength of gravity, it's the difference in gravitational strength across the body. And it stretches things, liquids, solids, anything that isn't perfectly rigid. Here's the thing, it's not just the ocean. Earth's solid rock flexes. The ground you're standing on rises and falls by about 30 centimeters twice a day due to lunar tides. You don't feel it because everything around you is moving the same way. Your body, the ground, the buildings. But it's happening. The whole Earth breathes with the moon's pull, twice every rotation. Tides aren't a water story, they're a gravity story. And the ocean is just the part that makes it visible. Now the mechanism that nobody pictures clearly because it requires holding a few things in mind simultaneously. Earth rotates once every 24 hours. The moon orbits Earth once every 27.3 days. Earth spins much faster than the moon orbits. That means Earth is constantly rotating underneath the moon, the ground spinning eastward faster than the moon moves in its orbit. Here's what that does to the tidal bulge. The tidal bulge, that stretching of Earth toward and away from the Moon, doesn't sit perfectly aligned on the Earth-Moon line. Because Earth is spinning, and because the oceans and solid Earth have friction and inertia, the bulge gets dragged forward by the rotation. Not far, but measurably, consistently ahead of the line connecting Earth's center to the Moon. Now there's an asymmetry. The near side tidal bulge, slightly ahead of the Moon's position in Earth's rotation, is closer to the Moon than the far side bulge. Gravity falls off with distance. The near side bulge pulls the Moon forward in its orbit with more force than the far side bulge pulls it back. The Moon gets a tiny gravitational nudge forward every rotation of Earth, every single day. In orbital mechanics, a forward kick, acceleration in the direction of motion, doesn't make you go faster in your current orbit. It pushes you to a higher orbit. More total energy, higher altitude, slower orbital speed. This is counterintuitive, but it's solid Newtonian mechanics. It's how spacecraft raise their orbits using rocket burns. So the Moon, receiving this tiny forward kick, climbs to a slightly higher orbit, a slightly greater distance from Earth, 3.8 centimeters per year. Simultaneously, and this is the other side of the same coin, the Moon's gravity pulling on that misaligned tidal bulge creates a torque on Earth, a braking torque. The Moon is pulling backward on the part of Earth that's been dragged forward. Earth's rotation slows. Angular momentum is conserved. Earth loses rotational angular momentum. The Moon gains orbital angular momentum. The recession and the slowdown are two sides of the same transfer. The ocean, by being a slightly imperfect fluid that gets dragged by Earth's rotation, is the mechanism. The beach you stand on, watching the tide come in, that's the engine. We don't just know this from theory, we've measured it. Apollo 11 landed on the Moon in July 1969. Among the instruments left behind, a retroreflector array, a panel of corner cube prisms that reflect light directly back to its source, regardless of the angle of incidence. Apollo 14 and 15 left similar arrays. The Soviets landed two unmanned rovers, Lunar 1 and 2, each carrying retroreflectors. Since 1969, observatories around the world have been doing lunar laser ranging. Fire a laser pulse at the Moon, time the return. The speed of light is known to extraordinary precision. The distance falls out, not approximately, to about 1 millimeter. And the distance grows by 3.8 centimeters every year, not estimated, measured, confirmed by over 50 years of continuous ranging data from multiple independent observatories. The retroreflectors on the Moon are among the longest-running physics experiments ever conducted, and they're still running. 3.8 centimeters per year sounds like nothing. It's the width of 2 fingers per year. The Moon is 384,400 kilometers away. This barely registers as a percentage. But run the clock forward a few 100 million years, and it matters a great deal. Run it backward 4.5 billion years, and it matters enormously. 4.5 billion years ago, when the Moon formed, it was close, very close. The leading theory for the Moon's origin, supported by the chemical composition of lunar rocks, the isotopic ratios, the dynamics, is the giant impact hypothesis. A body roughly the size of Mars, called Theia, collided with the proto-Earth. The impact was oblique, enormous, catastrophic. It ejected a vast quantity of material into orbit around Earth. That material, over a relatively short time, accumulated into the Moon. The Moon likely coalesced at a distance of perhaps 20,000 to 30,000 kilometers. It's now at 384,400 kilometers. It's traveled an enormous distance in 4.5 billion years, not through space, but outward, through the slow accumulation of gravitational nudges from tidal friction. At that early distance, the tidal force scales as the inverse cube of distance. Put the Moon at 1/10 its current distance, and tides are 1,000 times stronger. The early Earth's oceans. If liquid water existed, and it did surprisingly early, were experiencing tidal forces of extraordinary magnitude. Tides potentially hundreds of meters high, twice daily, and Earth was spinning much faster. The early Earth's day was roughly 6 hours. Faster spin, stronger tidal drag, faster recession. The Moon was receding much faster then, early in its history, and Earth was slowing more rapidly. As the Moon receded, the tidal forces weakened, the spin down decelerated. Both processes slowed together in a self-regulating way. The further the Moon got, the less energy the tides transferred, the slower the recession. It's been 4.5 billion years of this, decelerating the whole time, and the current 3.8 centimeters per year is a relatively slow phase of the process. The same mechanism, stealing the Moon's energy, slowing Earth's rotation, is written into the geological record. Earth's rotation is slowing at roughly 1.4 milliseconds per century. Tiny, but consistent and accumulating. 400 million years ago, the year was 400 days long. Not because the year was different, Earth's orbit around the Sun hasn't changed significantly, but because each day was shorter, about 22 hours. More days fit into the same orbital period. How do we know? Coral. Ancient coral fossils preserve growth rings, daily rings and seasonal bands. Count the daily rings between seasonal markers and you get the number of days in a year. Devonian corals, 400 million years old, consistently show around 400 days per year. Consistent with the measured slowdown rate, extrapolated backward. Tidal rhythmites are even more direct. These are sedimentary rock formations laid down by tidal action, alternating layers corresponding to daily tidal cycles, monthly cycles, annual cycles, all preserved in the rock. They're essentially tide gauge records going back hundreds of millions to over 1 billion years. They confirm the deceleration. The geological record has been keeping score. Earth's day is getting longer. The Moon is moving farther. Both measured, both recorded in the rock. The physics has been running consistently for longer than complex life has existed. There's a consequence of the Moon's recession that doesn't get mentioned enough. One of the most spectacular natural spectacles on Earth has an expiration date written in orbital mechanics. Total solar eclipses. The Sun is about 1.4 million kilometers in diameter. The Moon is about 3,500 kilometers in diameter. The Sun is 400 times larger than the Moon. The Sun is also about 400 times farther away. These two facts, the size ratio and the distance ratio nearly perfectly cancel out, giving the Sun and Moon almost identical apparent sizes in the sky. This is not a law of physics. It's not required. It's a coincidence of the current epoch of Earth-Moon-Sun geometry. The Moon covers the Sun's disk almost exactly, sometimes just barely covering it for a brief totality, sometimes slightly oversized, giving a longer eclipse. The near-perfect match is why totality is possible at all. The Moon is moving away. Its apparent angular size is shrinking, 3.8 centimeters per year, which translates to a decrease in apparent diameter of about 0.005 arcseconds per year. Barely anything. But in 600 million years, a geological eye blink in the context of the solar system's age, the Moon's apparent size will have shrunk enough that it can no longer fully cover the Sun's disk. After that point, no more total solar eclipses, ever. Only annular eclipses, the Moon centered on the Sun, but leaving a ring of solar disk visible around its edges. We are living in the precise window of cosmic time, a few 100 million years wide, during which total solar eclipses are possible. Before us, the Moon was too large and close. It would have covered the Sun with room to spare. After us, it'll be too small. The perfect eclipse is a fleeting accident of orbital mechanics, and we happen to be here for it. Follow this mechanism all the way forward, and there's an endpoint, in principle. The recession continues as long as Earth rotates faster than the Moon orbits. The torque exists because Earth's rotation drags the tidal bulge ahead of the Moon. When Earth's rotation rate eventually matches the Moon's orbital period, 1 Earth day equals 1 lunar month, the bulge aligns directly on the Earth-Moon line. No lead angle, no torque, no energy transfer. The recession stops. At that point, the Moon sits at roughly 610,000 kilometers from Earth, and one side of Earth permanently faces the Moon. Earth becomes tidally locked to the Moon, just as the Moon is already tidally locked to Earth. The Moon shows us only one face because it's already reached this end point. The Moon's rotation was slowed by Earth's tidal pull until it matched the Moon's orbital period. We're in the middle of the same process in reverse. The Moon is now slowing Earth's rotation toward the same locked state. The timeline for this is longer than the current age of the universe, several times longer. The Sun will exhaust its hydrogen fuel and expand into a red giant in about 5 billion years, almost certainly engulfing both Earth and Moon long before tidal locking completes. The theoretical endpoint exists. The path toward it is real. The destination is moot. There's a subtlety in the recession rate that deserves honesty. 3.8 centimeters per year is the current rate. It has not been this rate throughout Earth's history, and if you naively extrapolate it backward, you get a problem. At 3.8 centimeters per year, constant, the Moon would have been at the Roche limit, the distance at which Earth's tidal forces would tear the Moon apart, about 1.5 billion years ago. But the Moon clearly existed as a stable body well before that. The resolution. Ocean basin geometry is the variable nobody advertises. Tidal friction, the efficiency with which tidal energy is dissipated, depends critically on the resonant properties of ocean basins. The current configuration of continents and oceans creates unusually high tidal dissipation. The present recession rate is anomalously fast. As continents have drifted over geological time, as Pangaea formed and broke apart, as ocean basins opened and closed, the tidal dissipation rate changed. There were periods when the rate was much lower. The average recession rate over 4.5 billion years is significantly less than 3.8 centimeters per year. The geological evidence from tidal rhythmites confirms this. The rate isn't constant. It pulses with the rhythm of plate tectonics. This means the Moon's recession history is not a smooth curve. It's lumpy. Driven partly by orbital mechanics and partly by the arrangement of continents, which is itself driven by the churning of Earth's mantle, the Moon's orbit has been partially sculpted by geology. There's something worth sitting with at the end of this. 3.8 centimeters per year, the width of 2 fingers, multiplied by 4.5 billion years of patient, relentless, tide-driven recession. A moon that formed practically next door to Earth, inside what are now its own tidal disruption limits, has been walking outward ever since, not because of any exotic force, not because of any dramatic event, but because the ocean has friction and Earth spins. The tides at the beach, the twice-daily rhythm that coastal peoples have tracked for all of recorded history, are not separate from this. They are this. Every tide that's ever come in has transferred a microscopic amount of Earth's rotational energy to the Moon's orbit. The Moon is what it is, where it is, because of 4.5 billion years of tides. That's worth holding alongside the other thing. We live in the only window of the Moon's recession during which total solar eclipses are possible. The Moon has to be at just the right distance, not so close that it overwhelms the Sun, not so far that it can't cover it. For a few 100 million years on each side of now, the geometry works. You're alive in that window. So was every human who ever described seeing the sky go dark in the middle of the day and feeling something ancient and wordless. That window is closing, very slowly, 3.8 centimeters per year, slowly, but closing. We have retroreflectors on the Moon, 5 of them, left there by 3 Apollo missions and 2 Soviet rovers. We fire laser pulses at them, and we measure the distance to a millimeter, and every year the number is 3.8 centimeters larger than the year before. We're watching it happen in real time. The Moon moving away, millimeter by millimeter, year by year, driven by the tides, and us measuring it with lasers because we placed mirrors on the Moon with our own hands. That combination, the ancient, patient mechanics of gravity and spin, and the very recent, very human act of measuring it precisely, is what physics actually looks like when it's working. Not mysterious, not beyond reach, just extraordinarily careful attention to things that were always happening, that nobody had the tools to see clearly until now. The Moon is leaving at the rate your fingernails grow, and we know it to the millimeter.